Hi everyone, my name is Yihao. This is my course project presentation for EE591. I focus on Bach motion correction with variable density spiral trajectories. My personal goal in this project are first to get familiar with conventional motion artifact correction method and then implement a motion correction method for rigid motion artifacts from the perspective of MR imaging. Especially, I want to implement self-navigation techniques for motion correction with variable density spiral trajectories, and then explore efficient VDS trajectories designed for motion correction. Due to the prolonged time required for most MR imaging sequence, MRI is sensitive to motion. However, owing to voluntary or involuntary patient movement, the motion during the scanning is unavoidable. So, motion correction is an old but still important problem in current MRI research. Many kinds of motion can corrupt the image. Typical motion artifacts manifest as ghosting, blurring, geometric distortion, and so on. A comparison of brain image with and without motion artifacts is illustrated in the figure on the right. From the perspective of MR imaging, a basic idea for motion correction is to acquire multiple MR images dataset and estimate the motion in between through pairwise comparison. Once the movement of subject during the data acquisition process is estimated, we can undo the movement and correct motion artifacts. In this project, we mainly focus on self-navigation techniques. They estimate the motion from repeatedly acquired data from the same portion of K-space. The most popular method is propeller. It collects data in concentric rectangular strips rotated about K-space origin. The repeated samples, conventional called as interleaves, at the center of K-space provide inherent navigator information. They are acquired in short time and are considered as almost motion-free image. Following the same idea, motion correction method with VDS adaptive imaging trajectories are also proposed. A center-out imaging method, spiral MRI also has a natural advantage of rapid oversampling the center of K-space. Example of one VDS interleave and a stack of 20 interleaves are shown in figure on the right. Each interleave consists of variable density spiral designs to have higher inner spiral density and lower outer spiral density. At this point, a question comes into my mind. How does the variance of oversampled region affect the motion correction? Maybe a very small portion of K-space is enough. This would shorten the radar time and make the imaging process more efficient because the potential redundancy exists in every interleave. In conventional implementation, K-space covered by a circle is used as repeated sampling region. It is highlighted in red in the leftmost figure below. Well, can we use a small circle instead? Sure. Can we use drop the information at the center of K-space? Probably. To significantly improve the imaging efficiency, maybe we can use a very thin ring. In this project, I first implement self-navigation techniques with VDS adaptive trajectories for rigid motion correction. Also, I explored efficient VDS trajectory design for motion correction. The overall steps are first simulating data with in-plane rigid motion artifact, then estimate and correct the mismatching in between VDS interleaves. finally creating the stacked interleaves and reconstruction. We design a digital phantom for our experiment. It consists of objects which can be described by function in k-space. In between each interleave, we randomly rotate and shift the image. Besides, Gaussian noise are added to mimic the real scenario and make the correction task more challenging. Data are collected in k-space in 20 interleaves. Different repeated sampling k-space regions are tested. Here are some results. Origin images without motion artifacts are displayed in first row. From left to right, SNR of image increased from 10 dB to 40 dB. The second row shows the illusion of oversampling region and corresponding motion correction result. From this result, we can see our implementation of motion correction with VDS trajectory generally works. This motion correction result using a spiral ring. We can see the motion artifacts are properly corrected in different noise levels. Here are the motion correction results when using a very thin ring as repeated sampling region. From the results, we can find the quality of motion correction is obviously worse, especially when SNR is low. Quantitatively, results are used to summarize what we found. The right figure shows the relationship between rotation estimation errors and different repeated sampling region in different noise level. The right figure is for translation estimation error. The noise level are casted in horizontal axis and y-axis represents the error. The unit for rotation error and translation error are degree and millimeter respectively. We can find that when the effect of noise is significant, the more k-space covered, the better result we can get. If SNR is high enough, there is no difference between a circle and a reasonable thick ring in terms of rigid motion estimation errors. To some extent, we can conclude that a small repeated sampling region is feasible to handle motion correction tasks. Technical challenge I encountered in this project is that the setup for MR imaging is complicated. There are global settings like FOV, resolution, and corresponding choice of VDS trajectories affect each section of implementation. Besides, the organization of the experience to validate and test our intuition also takes effort. From this project, first, I learned how to set up framework to test motion correction method. Then, I also learned how to implement typical method for motion correction. Not limited to what I implemented, I also learned other motion correction techniques, which might be helpful in my future study. That's all. Thank you for listening.